Hello, good afternoon. It is a great pleasure to welcome you to the CRIAM webinar series. This is the fourth talk in the series, and the subject is a great challenge. Can the mining industry reduce its water consumption by 80%? I am really delighted to introduce our speaker today, Professor Peter Scales from the University of Melbourne, Australia. Hello, Peter.
Good morning from me and good afternoon to everybody.
Good morning. Dr. Peter Scales is an honorary emeritus professor at the University of Melbourne with over 30 years of experience in particulate and separations processing in the minerals and water treatment industries. His expertise and interest cover flocculation and agglomeration of particulates and the relationship to flow, rheology, and separations in devices such as membranes, thickeners, filters, and centrifuges. He is team leader for tailings processing in the newly formed Australian Centre of Excellence for enabling eco-efficient beneficiation of minerals, has published over 300 peer-reviewed articles, and is director of a private consulting company, Rheological Consulting Services. I must add that Professor Scales serves as a member of the Scientific Council of CRIAM for the last 7 years. So we appreciate that from Peter a lot. Let's start the talk, and you're most welcome, Peter. And
thank you, Pedro. Thank you. Good afternoon, everyone. I will share my screen, and hopefully everyone will be able to see my screen. May I start the talk by doing something that we traditionally do in Australia, which is acknowledge the lands of the traditional owners on the lands of which we meet. They're the lands of the Wurundjeri people, and I pay respect to their elders past and present and emerging. We often do this simply because we acknowledge that those people have been living on our lands for about 50,000 years. And today's talk is partially about the mining industry, but it's actually about sustainability. And sometimes we have to go back to our traditional owners to really learn about sustainability. So my talk title is, Can the Mining Industry Reduce its Water Consumption by 80%? And it's not a rhetorical question. It's actually, I think, a really, really important question. And at the end of this talk, I'll show you, hopefully, that if we don't introduce, or if we can't reduce water consumption by 80% in the mining industry, then I think we've got problems. The water use in the mining industry is very much related to how much water is used in a very wet process, typically in processing, but most importantly, about how much water is recovered at the end of that process, because if one looks at how much water is used, then the water lost to tails that goes to the tailings dam or the waste from the process represents the major loss of water. So if I want to actually change the amount of water we use in the mining industry, I've actually got to change dramatically what we do with our tailings. We've got to change the amount of water in there. And currently thickeners are what I call the workhorse of water recovery in that industry, where material from the process comes into the thickener and water is recovered off the top, and a solid slurry that's sent to a tailings storage facility comes off the bottom. That's not what happens in every mining operation, but it's pretty standard. And there's lots of different types of thickeners, and I'll talk to those because it becomes important to this task. There's high rate thickeners shown in a picture on the left and on the bottom left. There's deep cone thickeners on the top right, and conventional thickeners. And the main difference really, other than how we flocculate the material before it goes in there, is that these, the deep cones typically have diameters of about 15 to 20 meters, high rates up to about 45 meters, and conventional thickness up to about 120 meters in diameter. The reason that we need to reduce water in the mining industry is multitude. One of the main reasons is obviously from a sustainability point of view, we want to be able to use less water. But another reason is that one of the key things about storage facilities for tailings in the mining industry is that they are an ongoing liability to failure. And if they fail, they can cause catastrophic outcomes. And that's been seen around the world in Brazil and other places in the last few years. But if you look at the history, it's been happening since the start of mining. Storage facilities, as in this picture on the left, material is sent out to the storage facility and it is said to be dry disposed, which means that the material forms a very slight slope in the tailings storage facility. And even though there's water in the storage facility, it's said to be dry disposal, and I'll talk to that a little bit. So I think the big challenge for the mining industry is how do we make these storage facilities safer geotechnically, and eliminate the water in them and reduce the water use. I say those three things as challenges, but they're all, to me, the same challenge. Basically, if I reduce the water content in those tailings going out there by more than 50%, indeed, if I reduced it by 80%, I would then have a geotechnically safe storage. And in actual fact, I might not even have a storage. I might do it completely differently. So why do we do it the way we do? For the last 30 years or so, we've been sending flocculated material out to the tailings dam or the storage facility, and typically the suspension has about 10 to 20% minus 10 micron particles. Those particles form a network, and the network is continuous and interconnected, and we flocculate it to make it more permeable and stronger so that we can do those separation processes. But one of the problems is that that network has a strength that we have to apply pressure to overcome, to dewater it, to get the water out. And that strength goes up as 1 on the diameter of the particle squared. Therefore, if I have a system that's got 100 micron particles and I come to 10 microns, then the strength of that network doesn't go up by a factor of 10, it goes up by a factor of 100. And then if I made that 1 micron particles, it would go up by a factor of 100 again. Therefore, if I have a suspension of particles with a lot of minus 10 micron particles in it, then, and especially if I'm below 1 micron, the strength of that network can be very high. And as we move forward in mining and into the future, we're going to have more and more fine particles in our ore, which means that in actual fact, the strength of the network we're going to send out to the tailings dam is going to be greater and greater. And in actual fact, the solids concentration we send it out there is going to be lower, and the water use is therefore going to be higher. Therefore, if I look into the future at our current way we do things, then I have to conclude that we won't use less water, we'll probably use more water into the future. Therefore, we need to think how we're going to change that significantly. It's going to have to be a fairly radical change. To give you a bit of an idea of what that strength looks like of that particle network that's created that goes to the storage facility that holds all the water, we can measure the strength by a parameter that we call the shear yield stress. We measure it in a very simple rheometer or device where we have a vane, and hopefully you can see my cursor here, where we have a vane and we put it into a container and we rotate the vane very, very, very slowly. And we measure the torque on that device, and the torque goes up, it hits a peak stress and then fails. And we relate that peak stress to a shear yield stress in the system. How much stress did it take to make the system fail? So the system is initially networked, we put a stress on it, it hits a peak stress, and then it fails. And if I plot that failure point up, and I plot it as a function of solids concentration, I can do that for a wide range of mineral suspensions and tailing suspensions from around the world. And the next plot basically shows what that looks like. On the left-hand side is the shear yield stress, and along the bottom is the solids concentration. And this plot is for around about 30 different types of mine tailings from around the world. Over on the left are the fine ones, because I said that if you've got very, very, very fine particles in there, then the strength will be high, which implies that the strength at low concentration will be high. And over on the right are the coarse ones. And to give you an idea of this scale, 100 pascals yield stress is about the strength of tomato ketchup or tomato sauce. And up here is something that is closer to something like peanut butter. So we typically can pump materials that are less than about 100 pascals yield stress. So most of our operations in the mining industry are below 100. If I drew a line across, I would draw a line across at the 100. And in actual fact, for a particular mineral suspension, that defines my processing area for that suspension. And in actual fact, 50% solids here is about 1 ton of material for every ton of water. If I send material to the tailings dam at 50% solids, then I will have used 1 ton of water per ton of solids. If I'm going to save 80% of my water, I've got to shift this curve to the right. I've actually got to shift it up to where this other red line is on the right-hand side. And there's a material here that is a material that we call a paste backfill sample. And we would have to actually do slightly better than that, because if we operate under 100 pascals, then I've got to actually get to about 80% solids. In actual fact, I've got to get to better than that. And that suspension would be still full of water, so it wouldn't be geotechnically safe because it could still yield and flow under stress. And therefore, we would need to actually get the water out from between the particles, so it wouldn't be a wet system. So the challenge for the mining industry is how we take material that is at about 50% solids, and in some cases even less at the yield stress we operate, and move it significantly to the right. As I said earlier, the mining industry on average is moving to the left on this graph because materials are getting finer. To understand the limitations on mining, in actual fact, a lot of our processing is completely limited by what is on this graph. I can't pump much above 100 pascals with simple pumps. Therefore, if my material sits here, that's my processing limit, and that's my water use limit as well. In thickeners, what happens is that the feed comes in, we add a flocculant, the material settles down, water gets taken off the top, and we have a compression zone, and a rake rakes the material to to the center well and gets released and then goes to this tailing storage facility, flocculation becomes very important to how this operates, and the rake becomes very important to how it operates. And if we do a really good job, we can actually produce a paste material at the bottom. This material here has a yield stress of about 250 pascals to 300 pascals. This system is what we call rake torque limited, in the sense that the yield stress, once it gets past a certain point, the rake can't turn it and move material to the outside. Therefore, the rake in here is like a big rheometer. It's like a big yield stress measuring device. And in actual fact, we can relate what comes out to the rake torque and to the shear yield stress. So I can actually model a thickener, and we do that, and we measure the solids flux through the thickener as a function of underflow concentration. And if this is the curve, we can put an operational point here. If I flocculate, this curve goes up, but it actually goes to the left. So my operational point in terms of solids goes to the left as well. But either way, basically, I can relate the shear yield stress of the material that comes out the bottom to the shear yield stress curve that I can measure for the material. And I can pretty well define what is the maximum that can come out of the thickener simply by looking at a shear yield stress curve. So some people say to me, I need to model what the maximum that's going to come out of my thickener is. And I say, I already know, because I've measured the shear yield stress for your material. And in actual fact, if we go to different types of thickeners, the rheology is rake torque limited. And if actually I plot my yield stress curve as a function of the different types of thickeners, whether they be conventional thickener in red or a high rate thickener or a deep cone thickener, I can read off effectively what solids I can get to. I can also read off what my water recovery in mining will be. And typically the mining industry operates at 10 to 30 pascals of yield stress, and therefore that defines the maximum water recovery we're going to get. So that's how we operate at the moment. And if I was to put a square or an operational triangle or square or box on that graph, the Chilean mining industry operates pretty well inside that red box at the bottom of this curve. This is its operational window. And in actual fact, that operational window is moving to the left. Operationally, it recovers on average about 50% of the water, or 50% of the water in the suspension. 50% of the suspension is water, and therefore I use about 1 ton of water for every ton of ore. And I can get up to around about 0.67 of a ton, but I can get down to 1.5 tons of water per ton of ore. That's compared to places like the oil sands industry, which has a very, very high clay suspension. They use around about 4 tons of water for every ton of ore. So what are we going to do about it? So how do I save water and make tailings safe? If I listen to what's happening in the world, the answer is, well, we should filter it. We will take the tailings that comes out of the thickener, and before it goes to the tailings storage facility, I thicken it. Some of the issues here, the capex and opex on filtration, especially high pressure filtration, is very high. And I need to use high pressure filtration for a very simple reason. If I look at a filtration curve, and I've got one here on the left, this is time versus how much volume comes out of a filter. And this is for a material with 2 micron particles, so it's got about 10% 2 micron particles. I find that I dewater, and as I put more pressure on it, it compresses, but it doesn't actually desaturate until it gets to about 250 kPa. That means that I can't use vacuum filtration or simple filtration processes. I've got to use high pressure filtration processes that are very expensive. And if I don't use those, I can't get geotechnically safe tails. And in actual fact, even then I leave about 30% of the water behind and I don't get to very, very high solids. So I take 50% solids out of my thickener, I could possibly get to 70 to 75% solids in a filter. It's cost me a lot of money. And I've only saved 60% water. The solids is not completely desaturated and not geotechnically safe, but it is stackable and you can dry it. But I haven't actually really changed things significantly in terms of safety and in terms of the sustainability and the license to operate of the industry. So the first alternative I'm going to put up is that we need to actually take at least the 80% of material in our tails that can be dewatered very easily and separate it from the fine material. So my first basically statement is that we have to get a lot better at separations. And we already have technologies that can do this. In actual fact, we've typically used things like cyclones in the industry, but they will not get us there because as we go finer and finer and finer, the cyclone gets smaller and smaller and smaller. We have to use some new physics, and the new physics comes in what we call reflux flotation or reflux classification, where we use surfaces to actually enhance the separation process, and I'll show you that shortly. The other thing we have to do is float or do that flotation process a lot coarser so that we reject more material that doesn't go to tails. So that's a challenge as well. And the argument is that if I could have 20% of my material that I floated coarser, or sorry, if I floated my material coarser and 20% of my material got rejected earlier, if I could produce 70% of my material as free draining material because I've taken all the fines out of it, I would have a 10 to 20% of my material left that was extremely fine. It would be over to the left on my yield stress curve. But providing I could get that to 50% solids in filtration, then I could actually save 85% of my water. In other words, I would have 85% of my material that was geotechnically safe and only about 10 or 15% of my material that I really had to deal with that was difficult material. On the right here is a curve from what we call a reflux classifier, showing that in a reflux classifier, we can get a very sharp split between the coarse and the fine material, and we can do this at scale. In actual fact, there's about 120 of these units operating around the world at the moment, and they operate very, very effectively. And a picture of what they do is that we have a fluidized bed of material coming in. We run fluidized water up. It runs up into a series of laminar channels, and these are quite close together. And in actual fact, the surface enhancement of the settling in these laminar channels means that we can do very, very, very sharp cuts or de-sliming, even down to 5 and 10 microns in size. That's very difficult in a cyclone, but actually quite easy in a reflux classifier. And here's a picture of what comes out the top. This is the top here, and this is a picture of it. And you can see the flow is extremely, it's not turbulent, it's a laminar flow. And the length scale is less than a millimeter for that laminar plug flow. And these, I believe, are one of the future points of the industry in saving water. Why? Because we separate the coarse plus 20 micron material from the fine. So that's the first challenge. Float coarser and de-slime effectively And we can save at least 50 to 60% of our water straight away very easily. But what about the fine material? That's still going to be hard, and it's actually going to be finer than what it was in our normal ore. The current option is to optimize the flocculation and the flocculant choice and to filter that material, but that's never going to make the tailing safe. And in actual fact, we're just going to use more flocculant, and as the things get finer, it's going to get harder and harder. An alternative we probably need to think about is to use what I call agglomeration rather than flocculation. Agglomeration is used in pelletization and other processes where we take dry powder material and we replace the air with water. The opposite for the mining industry would be to take systems that are wetted with water and replace that with oil. If we could do that, we use capillarity rather than Van der Waals forces as our main driving forces, a lot stronger forces. And if in doing that, we can actually get rid of the water completely and have a very, very dense pellet. However, to do that, we need to be able to, in actual fact, we need to be able to make surfaces, all the surfaces hydrophobic. And we need to think about new molecules and new systems for making all of our systems hydrophobic. In flotation, we make the minerals that we want to collect hydrophobic, but this would require that we make all of the particles hydrophobic. And in doing that, very, very small amounts of oil could then produce very, very dense particulates. So the challenge is arming the surface to accept oil and changing our process thinking from flocculation to agglomeration. So that's 4 challenges. The last of them is that how are we going to filter that material? We typically use plate and frame filtration for very high pressures, which we would need. In the last 3 to 4 years, we've developed a device called a high pressure grinding roll dewatering device, where we use 2 rolls like in high pressure grinding with porous surfaces, and we suck the water through those porous surfaces. One of the benefits here over plate and frame filtration is that it's continuous, it can go to extremely high pressure, you can induce shear in the system, which is really important in actually breaking the network. You don't have filter cloths to blind, and the gap size can be related to the fineness of the material. We could also, because we don't have filter cloth, have oil in this system, which means that we could bring this technology and agglomeration together potentially to produce very, very, very high solid systems. So I've been through where the industry is currently at, which is that it's controlled by the rheology of the suspensions it actually deals with. My conclusion is that if we keep going the way we are, the changes we'll make are only incremental to the amount of water we use. And in terms of water recovery and in terms of safety, that really won't change the status quo. The reason I acknowledge the Wurundjeri people at the start of this talk is that they know about sustainability, and they know about that sustainability is about the entire system, not just one process. And in actual fact, this is about a system where we would have to reject more material at the start. We have to do effective desliming. We have to change from flocculation to agglomeration, and we have to change the way we filter. And by putting all of those together, we can actually reduce water use by 80%. We might even be able to do better than that. And they are current technologies, not technologies we have to develop, except for perhaps in the molecular area. So we have to get the chemistry, the engineering, and the process optimization right. And if we do that, I think we can actually change how we think and operate in the mining industry tremendously. And in terms of license to operate and in terms of safety, things would improve a lot. So thank you. I hope that's an introduction to some of the thinking that we're trying to do in the research centres that we work in and that CREAM is involved in as well. Thank you, Pedro.
Peter, thank you very much. Your talk points directly to issues about sustainability of the mining industry. We really appreciate that you share your ideas and the technology that you have been developed with us. I have a couple of questions, and the people in the audience can use the Facebook chat to send questions or comments, and I'll try to share those with Peter. For now, Peter, I would like to go back to the issue of making particles hydrophobic and adding chemicals to the underflow. And it seems a really good, great idea if we are able to devise a good, nice chemistry, green chemistry for that. So we end up with a hydrophobic particles, no matter what the size is. And so water is relinquished more easily in the end. I know that there are companies, at least one company, that is testing, I think they are testing some of these ideas in the north of Chile. I don't have much details of that. But essentially what they are doing is hydrophobizing the particles to get to make the catchment of water more easy.
Yeah, I think the important thing is that the flocculants we currently use in all of our dewatering processes, as we go finer, that we use more flocculant naturally, but we also get a stronger and stronger network that is harder and harder to get the water out. In other words, we'll never get to very high solids that way. The question is, how do we get to high solids? The answer is we have to reject that water. We have to make an extremely thin film, a nanofilm of oil on the surface, yeah, that rejects that water. And tumble growth agglomeration shows us that we can do that. And we can do it at actually quite low pressures. Tumble growth agglomeration, we just tumble it in a tumble bin and the water is rejected from the system, as distinct from the water is the problem in the system. But it does require, as you say, chemistry and hopefully green chemistry to do it. And how we make all the clays, etc., hydrophobic, I think is a great challenge. But I think it needs some of the work that you do, which is in simulation of molecular interactions with surfaces, along with engineering, etc., together to really change this. A lot of people say this is going to be too costly, and I say if we're only dealing with 10% of the material, we can use a lot more chemicals than what we use now, in the sense that we could use 10 times the amount, and so because we would be recovering a lot of water as well. So yeah. It comes down to this logic that says don't treat all of the tails the same way. We have to split it into the bits that are easy to process and the bits that are not, and then really attack the pieces that hold the water.
Thank you. Thank you. How about the technology that that you refer to? What is the status right now? Is Is it at a pilot scale or?
Which one? The high pressure dewatering roll?
Yeah.
It's a semi-pilot scale. We're still trying to find a met supplier that will scale it up basically and do all the testing on it. We've done a lot of lab work, etc. on it, but it now needs to be scaled up, and we're building the second prototype, which is going to be more of a machine for testing what its true energy use is, what its true throughput is, what its wear characteristics and everything are. It's based upon high pressure dewatering rolls, which are not high pressure grinding rolls, which are very well known in the industry. So the actual, what we call the base machine is already operating in the mining industry. We're taking the grinding rolls and we're replacing them with dewatering rolls. So the physics of how we apply the pressure, how we can get very high throughputs and everything is all really well known. It's just, can we do this in dewatering? We can go to very, very thin gaps, which is important because just as the shear yield stress goes as 1 on the particle size squared, which means that it goes up tremendously, then the dewatering rate goes as the gap size squared. So if I go down a factor of 10 in particle size, I have to go down a factor of 100 in gap size to keep the same dewatering rate. And all of our dewatering systems don't have an ability to change the gap size between the rolls, for instance, or in the plates. And so we have that flexibility. So both the reflux classifier and this machine introduce something that we need in the mining industry to deal with fine materials, and that is we have to actually produce another force or another variable into our system. We can't just have pressure and time. We have to have pressure and time and the ability to change the gap size. So in the reflux classifier, in changing the gap size from 4 to 2 millimeters, we get a tremendous change in the amount of cut for the same fluidization velocities, for instance. Currently, they've replaced very, very large scale plants in the mineral sands industry with a very small reflux classifier. You'd be surprised. It's just this massive plant has been replaced with one small machine. And that's the sort of thinking we need here. We have to actually change the throughput per unit area tremendously. And that's what we're trying to do. Not just trying to get to higher solids or something, but change the throughput per unit area.
Okay. Yeah, thank you. I think we have 2 classes of questions. A few of them are technical, and some of them has to do with the other part that you are guessing, I guess, is the relationship of the mining industry and their processes with the people. And so I'll go through the technical questions first, and then after that we can talk a little bit about how do we provide more confidence to the people in countries like Chile, and hopefully you share the experience in Australia. In that sense, okay.
Certainly the license to operate here is becoming very similar to the license to operate in Chile.
One technical question is, what would be the optimal approach to tailings management, especially in our central zone in Chile? I guess the one that is asking the question knows that you collaborate in projects in Chile. Considering the retreatment of old and new tailings, what kinds of projects should be considered to improve its processes?
The first thing I would suggest about either reprocessing old materials and or putting something new into our current process is we've got to change, we've got to be able to split the material. We've got to be able to remove the fraction of material that causes the yield stress. If I take a suspension of particles that has got no particles less than 20 microns in it, and I put it out on the ground, it will be free draining and get to 95% solids. Therefore, I think in any reprocessing operation, we've got, and the majority of the particles, at least 80%, are above 20 microns. So in thinking about reprocessing or in any process, the first step to me is that separation process. The next step is the dewatering process, but in reprocessing tailings and everything like that, we're trying to make them safe. We're trying to actually make a hill out of them rather than a tailings dam. We're trying to actually not have them as a legacy deposit. We have to make a small amount of material that we have to deal with long term, but the majority of material can be actually instantaneously made safe and made into something useful, even a product.
Okay, we have several questions, Peter. Just connected with this one, in your experience interacting with people in the mining industry in Chile, could you share about the efforts to optimize the use of water here in Chile and reduce the impact of emissions and waste?
I generally find that we're looking at optimization rather than radical change. And I'm not saying optimization is bad, but it's never going to solve the problem. So one of the key issues with any mining industry is once you've installed equipment and you've spent a lot of money on capital, to change that is a massive decision. And on average, people don't do that. They will renew a thickener 5 times rather than throw it out and put a different type of device in, because that's a huge risk. We already know that technology. So I think what I find on average, not just in Chile, but around the world, is that going to someone and saying, well, perhaps you shouldn't have installed that device is not going to get you very far. That's number one, because they've already spent the money on it and therefore you have to deal with it. But if I've got a 20 or 30 or 40-year-old plant and I say, what is my next major renewal? I find that the discussion on would I change out that technology for brand new technology is a very difficult one, because on average, the people know how to operate that plant at that site. And I think that is one of the really big challenges, is that we need to get some of these technologies into plants, even at small scale, to demonstrate to people what's possible and what can be done differently. Because I don't think it's going to happen at an old site. It's only going to happen at a new site. So I would argue for all the new mining operations in Chile, not the old ones, the question is, how are they going to be very, very different? And how are they going to demonstrate the way forward for the old parts of the industries that says, at some point I'm going to have to change. Am I going to put in the same equipment again, just a newer version of it? Or am I going to change completely? And so I find that on average, most of the mining industry is about optimization, not about change, because change is risky.
Okay, good. I'll read the next question. Someone says, thanks for the presentation, Dr. Scales. And the question is, the use of these technologies, those you referred to in your talk, will have a relevant impact on the recovery rates?
One of the problems with coarse flotation is you say, well, if I float coarse, am I going to reject material and that I shouldn't reject? And I think that is the challenge. I think the challenge for coarse flotation is to pick up more than what it would currently pick up, and then to grind less of that material into the next process. So a combination of reflux classification and reflux flotation, the coarse flotation and reflux classification, the implication is that we have a lower rheology flotation system, and hopefully the recoveries would be better. People generally find that if I deslime properly, my recoveries are better, not worse. Therefore, thinking about what my water use is going to be actually in the flotation process, not just at the end of the process. People say, well, I don't want to touch my flotation process because I do my water recovery at the back end of my plant. The answer is no. If you actually fix up your clay problem early and reject those clays and deal with them in the flotation process, people who have done that have found that their recoveries are better, not worse. So I think there's actually potentially benefits right the way through by saying, I'm going to recover a lot more water, I'm going to make my tailings geotechnically safe, you can potentially get better recoveries as well.
Wow. If the flotation process is going into a coarse particles process that will contaminate the concentrate with much more undesired particles, so what other processes can be applied to clean the concentrate besides flotation?
I don't think I said we're going to float. Sorry, perhaps a misunderstanding. The implication of coarse flotation is that I reject material early in the process. But currently we grind everything down to our flotation size and we float it to get our recoveries and our concentrates. The argument is that this would be a two-step process of a coarse flotation and then a rejection on a block of material, and then fine grind and conventional flotation. There's nothing that says that we don't do our conventional flotation step. Our separation in that step depends upon our grind size and upon our liberation size. So we're basically doing a coarse step to reject a lot of material that didn't actually need to be ground up very, very fine. That's the key to that coarse flotation step. It's not clearly the grade of the coarse recovered float concentrate is going to be poor. And that's the material that would then be reground and refloated to get to a very high quality concentrate. So coarse flotation is about energy reduction in grinding, and it's about less fine material going to tails.
Okay. One more technical question, and we'll jump to the social ones that some couple people here is eager to hear about that. Someone is saying that he knows about tailings being used as backfill paste, where it's mixed with a binder. Could be also an alternative?
Yeah, so it's a good question, this one, for not necessarily for open cut operations, but for certainly underground operations where you're using paste backfill. It's almost a requirement of paste backfill when you mix it with the binder and you put it underground and you need to get drainage in the underground situation, that in actual fact it is deslimed. Therefore, for backfill operations to deslime well and reject this -20 micron fraction, allows you to do more and more paste backfill. Currently, they use cyclones for that process, and because of the poor split, they probably only take about 30–40% of their material for paste backfill. But if we could split better, the argument is we could get about 80% of material into paste backfill, and in actual fact, the amount of tails would be tremendously lower. So I think part of this technological challenge is how we do this cleaner split and get more paste backfill and more putting material underground, because this material has to be free draining as a paste backfill material.
Okay. We are getting to the time passed very quickly, but I can't leave two questions, maybe a quick answer. Maybe answering this question I have many questions, Peter. Maybe answering this particular question will answer also the other more particular ones. Could you comment on the most relevant aspects in the design and construction of tailing deposit facilities?
Yeah, well, yes and no, I'll say. The most relevant thing is really whether or not you can truly get drainage and the material dry in your tailings dam. If you can't, then ultimately you have to deal with a legacy for a very long time in building that tailings dam, and the safety of the tailings dam, not just for the present, but for the next 50 and 100 years, becomes a really, really important aspect. Therefore, if I can't actually get to the point where the material is dry, not dry disposal as we know of it now, but truly dry, then my legacy is a very long one. And I think that's all I want to say about tailings dams, is that I'm not a geotechnical engineer, so I don't know how to build a dam. And they know how to build dams, and they know the difficulty of retaining their stability over a very long period of time, especially if there's earthquakes and things like this. And a lot of that comes down to, do we want to put material in there that is dry, or do we put material in there that is saturated? And the difference is tremendous in terms of the future. Yeah. It doesn't affect the past. We can't change the past.
Yeah. Peter, the tailings deposits have a bad reputation, no doubt about that, and generate tensions in the people. It is an issue that is present in Chile nowadays. We are dealing with that. We need to provide answers to the questions of the people. What initiatives have been implemented in Australia to improve people's relationship with the mining industry?
Not too many lately. There's been some problems lately, I would argue, certainly between the Indigenous peoples and mining of late. I think we were talking to someone from a large company the other day, and they've looked around the world at all of their tailings deposits, and they're looking at their risks and their safety and etc. And that's a tremendous job, because there's a lot of legacy deposits. There's a lot more legacy deposits or what they call inactive tailings dams than what there are active tailings dams. And I think a huge amount of that is basically spending the time, the money and the effort and actually communicating with the people about what the true safety of those dams is, and actually communicating with people around this. And in doing that, it helps. The problem is that a very, very large number of these dams, storage facilities, haven't had any real assessment and communication about them for a long time. And it's needed. And the problem is that they don't make money Tailings storage facilities don't make money, they cost money. And this is a problem for mining companies, is that their legacy, they have to spend money on legacy now that they didn't expect to have to spend. But when they do and they communicate, it actually does help. So I'm sort of hopeful that that process of the global tailings initiative that looks to reassess the safety and to communicate those aspects and to do the work to make these facilities safe will actually help that community response.
Okay, it's we have been in the air for about an hour, and that's the limit we have, and certainly we could be talking for a longer time, and so we expect to have you, Peter, in the future to talk a little more on the same subject or another new subject. Thank you to everyone that participate and joined Peter and this series of CREAM. And I'd like to say a special thanks to Professor Scales for his interesting, motivating talk, and his willingness to collaborate with us, with CREAM, all the time. Thank you to the audience, and thank you. I know that there are lots of students watching, and thank you, Peter, once more for your talk, your contribution, and your friendship with CREAM.
Thank you. Really appreciate it. And thank you for allowing me to put my views out there. Yes, thank you.
Okay, thank you. Goodbye.
Bye.
Goodbye.